This video involves looking at one method for deriving the general form of the Lorentz transformation for a boost in an arbitrary direction. It involves the use of vector methods. So let's start with an observer in the unprimed frame S, or just the frame S, and we have an event marked out by CT, the coordinates in Euclidean or Minkowski space, CT, X, Y, Z. So here's the event, here's a position vector R to that event, and the position vector is given by X, E1 plus Y, E2 plus Z, E3. So that's a position vector from an observer in frame S, and it records an event, the flash of a light bulb or a firecracker going off or some event. Another observer in another frame of reference, moving at constant speed with respect to the first, that's frame S prime, records the same event with different coordinates CT dash, X dash, Y dash, Z dash, and position vector R dash. So this is a different frame moving at constant speed relative to the previous frame S, a different frame, its position vector R dash, R prime, X prime, Y prime, Z prime. These are the axes. Now, frame S, the inertial frame S and the inertial frame S prime are moving relative to each other with the speed v. So S is moving relative to, S prime is moving relative to S with plus v, or S is moving relative to S prime with minus v, however you want to look at it. The velocity vector is given by this expression here, and you can see that it's just moving in an arbitrary direction. Now normally we look at cases that are in standard configuration where S prime is moving along the common X prime axis, or this X prime axis is parallel to this X axis, and it's moving at some constant speed along that axis. That's standard configuration. We want to now look at the general case where V could be, or the inertial frame S prime could be moving in any direction relative to S, any arbitrary direction. That's what we want to look at here, and how to derive the Lorentz transformation for the general case where this object's moving with some velocity at an arbitrary direction, in an arbitrary direction. So we have S prime. We can take the position vector in S, this one here, and we can recompose or decompose it into two vector components. So any vector can be made up of two vectors at right angle to itself, and we can choose this such that this parallel component, this component here, R parallel, is parallel to the velocity vector V. So this part here is parallel, R is parallel to the velocity vector, and this part, the perpendicular part, is perpendicular to the velocity vector. So we've chosen this decomposition such that this part here is parallel to the velocity vector V. This part here is perpendicular to the velocity vector V. And we know that R can be made up of the parallel part and the perpendicular part. Together they sum to give R. Now in the S frame we have the R is made up of the perpendicular and parallel parts, and in the S prime frame, an observer in S prime will give the position vector R prime as made up of the perpendicular part. They both agree on that, there's no change in that. But this parallel part is Lorentz contracted because S prime is moving relative to S, and so the observer in S prime sees the parallel part Lorentz contracted, hence this part here. The Lorentz factor is this one, but in this case now, instead of just a speed v along the x-axis, it's the scalar product of the velocity vector with itself, or the modulus of v squared over c squared. That's the Lorentz factor in the general case. Now the scalar product of r and v, which is going to help us find the vector projection, which we'll talk about shortly, r dotted with v is r parallel dotted with v, from this expression up here, plus r perpendicular dotted with v. Now by definition, this second expression here is 0 because these vectors are perpendicular to each other. So that r dotted with the velocity vector v gives us r parallel dotted with the velocity vector v. And that gives us the modulus of r parallel and the modulus of v. So it gives us the components of those two vectors. Now in standard configuration, if we had S prime and S in standard configuration where they're moving well to each other along their common x-axes, then T prime would be gamma times T minus x on V. C squared, the scalar V, because it's moving along the x-axis in one direction only, so it'd be a scalar. If we were to generalize this, then T prime becomes gamma times T minus R dotted with V over C squared. Now we can expand this out, so we get T prime is gamma times T. But here, we get the x component of the position vector with the x component of the velocity vector, and here it is, x times V subscript x over C squared, and minus y times V subscript y over C squared, minus gamma times Z times V subscript Z over C squared. Multiply both sides by C, factor of C. We get C times T dash is gamma times CT, minus gamma times x times V subscript x over C, minus this part here, and minus this one here. Now, we can tidy that up even just a little bit further, where it's conventionally used beta, so we get C times T dash is equal to gamma times C times T, minus gamma times x times beta subscript x, minus gamma times y times beta subscript y, minus gamma times z times beta subscript z. Now beta subscript z is just V subscript z over C, beta subscript x is V subscript x over C, and similar here, beta subscript y is V subscript y over C. Alright, next bit now. R dash, R prime is R perpendicular plus gamma times the parallel bit minus VT. This is the Lorentz contracted part. But the perpendicular part can be rewritten in terms of the original position vector minus the parallel part. And so we can substitute that into this top line to get R prime is R minus R parallel plus gamma times R parallel minus the velocity vector V times the scalar T. We go next line over. Now, let's have a look at some properties of the scalar product and vector projection. So R parallel, the part of the vector R dotted with V gives mod parallel part of R times mod V times cos 0 degrees, because they're parallel to each other, so the angle between them is 0, and that gives us this object as we found earlier. Now from here, we could rewrite that and say the modulus of the parallel part is just this bit divided by this scalar here, which is what we've got here. So that gives us, but we've also found that R parallel, that part of the vector dotted with V, is the same as the original vector dotted with V. So this, the components here, the scalar part of the vector R parallel is R dot V over the modulus of V, and that implies that the vector then, the part of R that's parallel to V, can be expressed as its scalar, the absolute value of it, the modulus of it, the scalar part of it, times this unit vector here, because this is the vector V over the modulus of vector V, so this gives us a unit vector in the direction of V, which is, as we know, parallel to the parallel part of R. So the parallel part of R, that vector part, is its own scalar product there, its own modulus there, its magnitude, times this unit vector here. And so we can rewrite now the parallel part of R, of the vector R, as this object times this object here. So that's the vector projection of R in the direction of V, and gives us this parallel part. So the vector projection of the vector R in the direction of velocity vector V gives us this parallel part of R. Now, coming back here, R prime is this object as we found earlier. Now, we can just rearrange some terms here. We can collect this minus R in here. We can have gamma minus 1 times the R parallel part. Okay, and then next line down, R plus gamma minus 1 times the R parallel vector can be replaced with what we found on the previous page, which was this whole expression here. Now, minus gamma times VT. So that's minus gamma VT plus R plus gamma minus 1 times this object here, just rearranging, so simply taking that last term and bringing it to the front. Okay, just tidying this up just a little bit more, take out the modulus V here and just stick it over here, over this part here. It's this part that will be interesting in the next bit. So I'll repeat that last line. So expanding out the terms of the previous expression, shown again below here, gives, so here's the bit from the last line from the previous page. We want to expand this out. So we want to start with the x component in the r prime frame. So that's x dash, x prime, is minus gamma, the x component of v, and then the x component of r. And then here we want the x component of v, there, and there. But the bit in brackets, well, order of operations, we need to evaluate it. So what happens is that in here, this gets totally evaluated. X times vx, y times vy, z times vz, all multiplied by this gamma minus 1 factor, and then multiplied by just vx, not the other components, just vx. So what we're looking for is the x component, so the x component here, x prime, x component here, vx, x component here, x component here, which is these vx's here, but then this bit here needs to be expanded out in full. Order of operations, if you like, do what's in the bracket to get that done first, then evaluate the rest. That's how we end up with, that's one way of looking at it there. Y prime will be minus gamma vy, y, vy, vy, and then the scalar product again in here. Z prime will be vz here, z, vz here, vz there, and the scalar product in here, multiplied by the gamma minus 1 factor. Next line, now, next page over, we're going to try and tidy this up a bit. We're going to use beta vector form as v subscript x over c e1, plus this term, or it can be more conveniently written as beta subscript x e, and then each of the basis vectors, just there. Now, from a few slides back, ct dash or prime is this object here. We've already expressed that using the betas. X prime now becomes minus gamma beta x times ct. We put an extra c in there because the beta x is a vx on c, so we've added a c there. And we've got x, we put betas here, that's vx on c, but then beta squared will be have a factor of c squared underneath, which will cancel that out. And this means the same thing, expresses the same thing as on the previous page. End up with the previous page. So this is the more usual form for expressing it. And we can go one step further by tidying up because beta z and beta z can go together. Beta y, beta z could be multiplied out there. And we'll see shortly when we tidy this up. Alright, we can take this into matrix form where we pull out ct x, y, z, and over here ct dash x dash y dash z dash. And here in this bracket is this 4x4 matrix, which is the Lorentz transformation, or the general Lorentz transformation for a boost in any arbitrary direction. Now if you just wanted a boost in the x direction, not in the y or z, then beta y and beta z will drop out to 0. So that'll go to 0, that'll go to 0, that will. These ones along here will go to 0, as will these, and those, and you'll just be left with, and they'll go to 0. Anything beta subscript z or beta subscript y will go to z, will go to 0, sorry, and beta subscript x will be the only one, because if you're having a boost in the x direction as in standard configuration, the only terms you'll get will be this one, this one, this one, this one. This will be a 1, and that'll disappear. This will be a 1, or that'll disappear. The rest of these here, and here will be 0, as with these and these, and that will give you a standard configuration. Otherwise, for a boost in a general direction, this is the matrix you want. We can express this in a more compact form. This is a mixed tensor of rank 2, mixed because it has a contravariant index or an upper index and a covariant or lower index. And using generalized coordinates, x mu represents ct x y z, and x mu dash ct dash x dash y dash z dash. So that's the general Lorentz transformation using a vector method to arrive at it.